This is the first lecture of 21st century electromagnetics. And what I mean by 21st century electromagnetics, there's a lot of hot topics now. There's metamaterials, photonic crystals, all kinds of crazy stuff, 3D printing. And it appears that electromagnetics in the coming decades will look a lot different. This course is really designed to teach you what electromagnetics could look like in the coming decade and to give you the tools and concepts that you can design electromagnetic devices in the coming decades. So this lecture are just some preliminary topics in electromagnetics. Most of this you've seen before, so in a way this lecture is also supposed to serve as a transition between last semester and this semester and just get us on a common footing. Maxwell's equations. Here's a big summary of Maxwell's equations, and we will make extensive use of Maxwell's equations this semester like we did last semester. And here is a summary of the equations, the different parameter definitions, the units, etc. And of course, no discussion on classical electromagnetics is complete without the Lorentz Force Law. We will not make use of this law this semester. We will use almost exclusively Maxwell's curl equations, but it wouldn't be complete without the Lorentz Force Law. Putting all of Maxwell's equations together, what we'll call Maxwell's equations, and the constitutive relations is summarized here. And as I keep mentioning, notice Maxwell's equations do not contain any materials. Maybe one exception this current term, we could argue there's a conductivity in there, but there's no permeability or permittivity in Maxwell's equations. That happens in the constitutive relations down here, where the D field and the E field are related through the permittivity, and the B field and the H field are related through the permeability. Now, very often the constitutive relations are substituted into Maxwell's equations, and what we're left with are just called Maxwell's equations. But for sure, Maxwell's equations themselves don't contain permittivity or permeability. So Maxwell's equations don't directly tell us how the fields interact with materials. That comes from the constitutive relations. So one way we could summarize this as Maxwell's equations is what causes the fields, what produces them. A time-changing D field, for example, causes a circulating H field, or if we can induce the circulating H field, we'll get a changing D field. But how the fields interact with materials, that comes from the constitutive relations. Like last semester, we discussed two types of boundary conditions, and to differentiate them, we called one the physical boundary conditions, and the other we call numerical boundary conditions. The numerical boundary conditions were we were writing some kind of equation on a grid, and at the edge of the grid we needed values from the outside, and we needed to know what to do about that. How we handled that we called a numerical boundary condition. Well, here's physical boundary conditions, and there's a lot more than what I've summarized here, but the main ones we'll use this semester is that the tangential component of the electric E field is continuous across the interface. Likewise, the tangential component of the magnetic field H is continuous across the interface. However, with E and H, their normal components are not continuous across the interface. But what is continuous is the product of the permittivity and the normal component of E. That product is continuous across the interface, and we could say the same thing for H. The permeability times the normal component of H. That product is continuous across the interface. Another one we use a lot is that the tangential component of the wave vector is continuous across an interface. Now we can write boundary conditions for D and B. If we need them, we'll talk about them. But these are the main ones we'll use this semester. Just like last semester, these were the main ones. Maybe this is a little bit of a force fit, but there is a discussion we need to have. Last semester we talked about finite differences on a staggered Yee grid. Here we need to talk about matrix derivative operators on a co-located grid, because we need to get you guys going on developing a an equivalent of Yi-der, but something to construct derivative operators for a scalar or co-located grid, because we'll need that later in the semester. We don't need it immediately, but this seems like a convenient place to put it. Remember how we did finite differences and how that compares to the traditional way that it is implemented. So we have some governing differential equation. In the conventional finite difference method, we approximate the finite differences. Really, all the terms in this equation we approximate with finite differences. Then we go from here directly to constructing the matrix equation. Now, for only one simple equation like this, that's a pretty simple step. But if we have many, many terms, many order derivatives, and maybe a set of equations, going from this to our big matrix can be a very, very difficult task. Well, once we have that, it's pretty easily solved. But instead, what we did, we jumped straight from a differential equation to that differential equation in matrix form. And we did that because we constructed functions which would build these derivative operators for us, and we looked at this one term at a time and built matrices and column vectors. And so once we have those basic tools, going from a differential equation to the matrix form is almost effortless. And then we factor out all of the square matrices and our knowns and unknowns, and we end up at matrix form. That's a very clean, straightforward step, and then we can solve it just as easily. So on the left, the conventional way, in my opinion, is much more difficult, much more tedious, and on the right is every step is very easy. So for co-located grids, or a scalar grid where we only have one function, it's not all set from anything else, here are the main finite difference approximations that we need. We need first order derivatives in the x and y directions, and we need second order derivatives in the x and y directions. And we did derive these last semester, but these are the basic finite difference approximations we'll need for our scalar or co-located grid. Sometimes you'll see what's called atoms, and it's just a graphical way of drawing where you're collecting the terms from to estimate your finite differences. We won't use them this semester, but I want you to have to have seen these. So if you see them in literature, you'll know what they're talking about. Well, like last semester, these finite difference approximations have problems when we're at the edge of the grid. For example, if we are at the low side of the grid, we need to take the function value from the next cell minus the function value from 2 cells previous, which in this case would be outside of the grid. And so Dirichlet boundary conditions, we just assume that they're 0 and then divide by 2 times the grid spacing. Well, we could talk about that for first and second order derivatives, and these are the finite difference approximations where we set the troubled terms to 0 to implement the Dirichlet boundary conditions. We could just as easily talk about periodic boundary conditions. Well, over this first example again, we have the function at 1 cell to the right minus the function at 1 cell to the left. However, that's not there, but we can reach the complete other side of the grid. We would want an x sub 0 here. That doesn't exist. So we reach to the far right-hand side of the grid, and we have x sub big NX. And so if our function f really is periodic, it should be valid to do that. And this slide summarizes all of the periodic boundary conditions for all the finite difference equations that we'll need. Now we need to talk about a new type of boundary condition, which is a Neuman boundary condition. A Neuman boundary condition we use for things that are not periodic, and we just want them to sort of continue into the boundaries. We know it's not going to repeat. We know it's not going to go 0. We want it just to sort of keep going and continuing. Strictly speaking, a Neuman boundary condition says the first order derivative is a constant at the boundary. If the first order derivative is a constant, then the third, fourth, fifth order derivatives are all 0 at the boundary. So to visualize what's going on, let's say we have some crazy function. Well, if we are saying the first order derivative is continuous across the interface, what that really means is we look at the slope at the edge of the grid, and we're assuming that just continues off straight. Now we know that's not necessarily reality, but that is a pretty good approximation, and it lets functions just sort of seem to continue at the interfaces. So here's an example that we're going to do later this semester when we start spatially varying gratings. Well, this pattern, it doesn't repeat left and right. It doesn't go to zero. It just keeps kind of going off to the edge of the grid. Without using a boundary condition like Neumann, we wouldn't be able to generate geometries like this at all. So here's the details. We start with our basic finite difference approximation for a co-located grid. We're not on a Yee grid now. First order derivative in the x direction is the function value from the next cell minus the function value at the previous cell divided by 2 times the grid spacing. Okay, now we have a problem at the left-hand side of the grid. Function value at the next cell minus function value of the previous cell, this does not exist, over 2 times the grid spacing. Well, we don't want to use Dirichlet, we don't want to use periodic, yet somehow we need to approximate the derivative at x equals 1. Notice we're actually spanning 2 grid cells to calculate that. Well, instead, at the very edge of the grid, let's use a finite difference approximation that only uses 2 cells. So it would only be the function in the next cell minus the function in the same cell divided by delta x. Well, right away we can see we're not using a central finite difference. We're actually using this to estimate the derivative at f1. So we're taking a small hit in accuracy, but this really is all that we can do. Likewise, on the far side of the grid, we have the derivative at the next cell minus the derivative in the previous cell over 2 times the grid spacing. Well, this does not exist at the far right-hand side of the grid. So instead, we only look at the 2 adjacent cells. We look at the function in the cell we're interested in minus the function at the previous cell divided by just 1 grid spacing. So we're only spanning 1 grid cell here to calculate the derivative at the edge of the grid. When we do this, we call this Neumann boundary conditions. And what about the second order derivatives? Well, if the first derivative is a constant and the second order derivative is the derivative of the first order derivative, we get 0. So in order to enforce Neumann boundary conditions, which says the first order derivative is a constant, then the second order derivatives are forced to 0 at the boundary. So here's the Neumann boundary conditions described at the boundary. So this would go with the previous set of slides where we did a similar thing with Dirichlet boundary conditions, periodic boundary conditions. Here's how we do the Neumann boundary conditions. And here's some examples of derivative operators using the Neumann boundary conditions. This is the first order derivative in the x direction for a 4x4 grid. And so when you're writing your own function in MATLAB, you can use this to benchmark. There's also codes available on the website. There's 2 of them. There's a FDDER_test, and you can use that to test your function to make sure it works. The other thing I provided was an FDDERS, and this works exactly like your FDDER function that you are going to use, except it only does very, very small grids. It'll error out if we try to do a larger grid. But what it lets you do is construct derivative operators for small grids to check against your answers to make sure that you're doing it correctly. Here's the first order derivative in the y direction for a 4x4 grid using Neumann boundary conditions. Second order derivative in the x direction, again using Neumann boundary conditions. Remember, the second order derivative now is forced to 0 at the boundaries where we have Neumann boundary conditions. And the same thing, second order derivative in the y direction. Okay, so that was brief. If that was your first introduction to matrix derivative operators, you'll definitely need to go listen to some lectures from the Computational Electromagnetics class. Given that background, what we just talked through was, I think, sufficient to understand that and go ahead and try to implement that. So with that out of the way, let's get back to the electromagnetics. Let's talk about polarization in a bit more detail than we talked about last semester. So polarization refers to what is happening with the electric field. We don't look at the magnetic field at all, and it turns out whatever's happening to the electric field, we would have the same polarization if we defined it in terms of the magnetic field. But it's usually the electric field is the one that interacts with materials, most commonly with metals and dielectrics, and so that's the more physical one most of the time. So we define polarization just in terms of the electric field. Now, if the electric field is restricted to a plane and only oscillates up and down within that plane, we call that a linear polarization. Imagine your eyeball over here to the left looking down this wave coming at you. You would see the electric field only oscillating in one direction, so we'd call that linear polarization. We can also have something called circular polarization. Again, your eyeball's over here to the left. You're looking down at the wave coming towards you, and if you could see the electric field, a circularly polarized wave, you would see the electric field rotating around that axis like a hand on a clock. So let's talk more about this. The rigorous way mathematically to handle polarization is like this. Let's say we have a wave traveling in the z direction. That means we will have a polarization vector, that's the amplitude of the electric field, in some direction. Now, since our wave is traveling in the z direction, our polarization has to be perpendicular to that and will be in the xy plane. So we can, in general, express our polarization vector this way, and it's restricted to be in the xy plane. Now, if we have a wave traveling in the k direction, so not in the z direction anymore, P and K have to be orthogonal to each other for sure. So we will pick two unit vectors, A and B, and those are the two orthogonal directions that are orthogonal to K, and now we can write our polarization vector this way. Very similar to what we did up here for the x and y directions, but now it's the A and B directions. So A and B and K are all at 90 degrees with respect to each other. And looking at A and B, if we are oscillating only in A or only in the B direction, our waves would look like this, and we would have two linear polarizations. And it turns out any sum of these two in any amplitude, whatever, will always give us another linear polarization. If we have both at the same time with the same magnitude, we have a linear polarization at 45 degrees between the two. Circular polarization. Well, let's put this in the same framework we had on the previous slides. We have a wave traveling in the z direction. P, we know, has to be in the xy plane. Well, the polarization vector now takes this form. To be a circularly polarized wave, we have to have two orthogonal components. Those two orthogonal components have to be the same magnitude, and they have to be exactly 90 degrees out of phase. So we put a plus or minus j in here, multiplying either the x or the y. So we have two components that are orthogonal. They're the same magnitude and 90 degrees out of phase. When that's the case, we have a circularly polarized wave. Well, we can write a similar thing for a wave traveling in an arbitrary k direction. And again, we have our same A and B directions, but they're the two orthogonal directions. They have the same magnitude, and they're 90 degrees out of phase. One way we can think about this is that there is no circular polarization. There's only linear polarizations. And what a circularly polarized wave is just simply two linears that are 90 degrees perpendicular and 90 degrees out of phase. And when that's the case, if we were to look down the barrel of the gun, the thing's shooting this electromagnetic wave at us, so our eyeballs might be over here and we're looking down this direction. If we could see the electric field, we would see it rotating about this axis. And of course, for circular polarization, it does perfect circles. Now, optics people and electrical engineers define polarization differently. If the wave is traveling, in this case, from left to right, if we are looking at it from the receiver's perspective, so our eyeballs looking down the barrel at it coming at us, the wave coming at us, and we look at the behavior of the electric field, that's how IEEE and electrical engineers view polarization. Optics folks look at it the other way around. The eyeball's over here on the left, and they're looking at the wave traveling away. And we look at the way the electric field rotates around that axis. And so optics folks and electrical engineers have the opposite definitions of polarization. What an IEEE journal would call right-hand circular, and an optics journal will be called left-hand circular. So keep that in mind. But if the electric field appears to be rotating counterclockwise, that would be called left-hand circular. If it's rotating clockwise, that is a right-hand circular. In this class, we will take the IEEE perspective. Our observation will be on the receiver, wave traveling left to right, and we're looking back at the wave coming at us. We look at how the electric field is rotating. Counterclockwise is left-hand circular. Clockwise is right-hand circular. We didn't mention a slide, or we didn't provide a slide here, but anything other than linear or circular is elliptical polarization. And this is just a slide that summarizes all the different linear polarizations. Linear along X, linear along Y, right-hand circular, left-hand circular, and then of course everything else is elliptical. We mentioned this before, but the red and the blue curves here are our two orthogonal polarizations. So we have red electric field oscillating up and down, or I'm sorry, the blue is an electric field oscillating up and down. Red, we're going back and forth. If we add these two, it turns out we get an electric field oscillating what we're showing in green. It's at the 45-degree angle. If we change the amplitudes of one of these waves, it looks like a linear polarization but at a different angle now. If we take these two polarizations in red and blue have to be in phase. As soon as we take them out of phase, it is no longer linear. It becomes circular or elliptical. If we take two linearly polarized waves that are at 90 degrees with respect to each other, so we're showing that on the left, and we also make them 90 degrees out of phase, what we get overall is a circularly polarized wave. Because if we could see the electric field directly, we would see that it would rotate around the axis where the wave is propagating. So this gray bold line here, that's the axis. If we were looking backward on this, we would see this rotating. So if we add two linear polarizations that are the same magnitude and 90 degrees out of phase and orthogonal to each other, we get a circularly polarized wave. Likewise, if we take two circularly polarized waves and add them together, we get a linearly polarized wave. And so the way to think about that, on this axis, when red and blue are both positive and pointing up, they're both pointing up. So our electric field definitely ends up pointing up. Over around here, the blue circularly polarized wave is pointing to the right, the left is pointing, or the red is pointing to the left, and the two cancel. So in fact, we end up getting a zero here. And in fact, we never get any overall electric field pointing off the axis. It's always just up or down. So two circularly polarized waves give us a linearly polarized wave. And if we can control the phase between these two circularly polarized waves, in fact, that would control the orientation of the linearly polarized wave. As let's say the blue wave goes out of phase with the red, this linear polarization would tilt over. And in fact, it would rotate around the axis depending on the phase between the right and left-hand circularly polarized waves. So why is polarization important? Well, different polarizations behave differently. We saw last semester in Computational Electromagnetics, when we were analyzing things in two dimensions, we had an E mode and an H mode. These are your two orthogonal polarizations, and they behave differently. We can model the same device with same everything, but the two modes come up with different answers, different diffraction efficiencies, different reflections, and that's because different polarizations behave differently. Also, orthogonal polarizations won't interfere with each other. Sometimes we want interference. Sometimes we're basing devices and depending on interference. But if they're orthogonal, we won't get the interference and we won't get the behavior that we want. Other times we don't want the interference and we actually want orthogonal polarization. If we're analyzing devices that are many thousands of times larger than the wavelength, then it turns out polarization really isn't that important. So in optics, when we're doing things like ray tracing through lenses, those lenses are millions of times larger than the wavelength, and we can ray trace very accurately without considering the polarization. But when the structure is on the same order as the wavelength, again, the polarization is very, very important. The Poincaré sphere provides a graphical way of mapping a polarization to a point on a surface. So we have a sphere, and every point on this sphere is a polarization. The north and south poles are right and left-hand circular polarizations exactly. As we go around the equator, we map out all of our linear polarizations. And we can start off at 0 linearly polarized. We come around 90 degrees. We end up with a 45-degree linearly polarized. And we come around to the opposite side. We're 90 degrees linearly polarized. And so on. We go all the way around, and we would be back with the same orientation right here. So the equator on the Poincaré sphere is a linear polarization. And of course, anywhere else on the sphere is elliptical. Now, the utility of the sphere is that if we're at opposite sides, that's orthogonal polarizations. Those will not interfere with each other. So right and left-hand circular, they're at opposite sides of the sphere. They won't produce interference. 0 degree linearly polarized and 90 degree linearly polarized. Clearly orthogonal, they won't interfere. Well, it's a little less obvious if we have an elliptical polarization, but we can map that on the sphere and real easily see the other polarization we're considering, and if they're on opposite sides or close to it, they won't produce interference. So the Poincaré sphere is just a nice graphical way of plotting polarization, and we can see some interesting things. And it becomes very intuitive of what's orthogonal. When we talked about linear polarization, we just arbitrarily chose directions A and B because we really had nothing to base it on. Well, suddenly if there's a device involved, the choice of A and B are two orthogonal directions for our linear polarizations. They can become important. And this is where we start talking about TE and TM waves. So as soon as you hear TE and TM, there absolutely has to be a device involved. It doesn't make sense to talk about TE and TM of a plane wave in outer space. That because they're all transverse electromagnetic, TEM. So when you hear TE and TM, there's got to be a device, and somehow we're defining these two orthogonal polarizations relative to the device. So the most common configuration is just an interface. We have, let's say, air and some kind of material, and we've got a wave coming in along this black vector. Well, the surface normal and this incoming wave vector, those are two vectors, and they form a plane. The plane that they define is called the plane of incidence. The polarization within that plane of incidence we call the TM polarization. Sometimes it's called the parallel polarization or the P polarization. There's another polarization that's perpendicular to that plane of incidence, and that's the TE polarization, or sometimes called perpendicular or S polarization. But we end up with these two polarizations because when we analyze transmission and reflection at the interface, it turns out it's those two polarizations that behave differently, and it decomposes into those two very nicely. We won't go through that math, but we will use the conclusions. So let's jump into that. Let's talk about scattering at an interface. We have one phenomenon, reflection. We have an incoming wave and it reflects. And in fact, the angle of reflection equals the angle of incidence, although we're going to talk about that in a few slides. but angle of reflection equals angle of incidence. We also have refraction. We have an incoming wave and it bends, and it actually transmits at a slightly different angle. That's called Snell's law. That's what describes refraction at an interface. So Snell's law is real simple. The law of reflection is real simple for calculating angles, but if we want to know how much of the wave reflects or how much of the wave transmits, we have to use something called the Fresnel equations. And the Fresnel equations are different for the two different polarizations because they behave differently. We have reflection coefficient for the TE polarization, the transmission coefficient for the TE polarization, and notice they're a function of the impedances on either side plus the angles on either side. And of course the two are related to this equation. And we have a very similar but slightly different equations for reflection and transmission for the TM polarization. But we use these equations to calculate how much gets reflected and how much gets transmitted. And using these is a good way to benchmark codes. If you're modeling scattering at an interface, we can calculate theoretically what the reflection and transmission should be, and hopefully our models get those same results. When our wave is coming straight in at an interface at normal incidence, things simplify a lot. And in fact, our reflection and transmission coefficients for the two polarizations become the same thing, and our equations simplify considerably. So very often, when we're using this to measure material properties, for example, people will just do this at normal incidence because it's a simpler configuration. Well, if we look at the Fresnel equations, we can see some special cases. One is called the critical angle. And it turns out we can choose an angle above which the reflection coefficient, the magnitude of it, will always be 1. And it won't get any smaller. So in other words, 100% of our power is being reflected from an interface. This happens when we're going from a material with a high refractive index to a material with low refractive index. So glass to air, for example, and we get 100% reflection. And waveguiding is built on this. We also have something called the Brewster's angle. And this is where one of the reflection of one of the polarizations goes exactly to 0. So that means that particular polarization is 100% transmitted. Well, what's neat about that is if it's 100% transmitted, whatever gets reflected must be purely the other polarization. And so people use this to make polarizers. And so we have a Brewster's angle for the TE polarization and a Brewster's angle for the TM polarization. Most of the time, our materials don't have a magnetic response, and in fact, their reflection, that never happens. So we usually don't even talk about a Brewster's angle for TE polarization when we're ignoring the magnetic response of a material. But the TM polarization does have a Brewster's angle. And in this case, the TM polarization is 100% transmitted, so whatever reflects is a TE polarized wave. So polarized sunglasses are built on this concept. The sunlight bounces off the water at an angle maybe close to the Brewster's angle, probably close. And so the TM polarization transmits into the water, so what is reflecting off of the water, the glare, is a TE polarization. So it makes sense. Let's come up with these linearly polarized sunglasses that block the TE polarization because that's what's reflecting, and what's left is the TM polarization. And you're looking at things coming up from underwater or from the other side of glass. So that's how we reduce glare. Anytime light or an electromagnetic wave reflects off something man-made, it tends to come off rather polarized because of this Brewster angle effect. So some final notes on reflection at a single interface. It is fundamentally a change in impedance that causes reflections. I could choose two different materials that have different dielectric constants and there won't be any reflections. I can choose two things that have the same dielectric constant and there will be reflections, because the dielectric constant is not the only thing that determines impedance. There's also the permeability. Snell's law quantifies the angle of transmission, and Snell's law is independent of the polarization. So the angles that things happen is independent of polarization, but the amount of reflection and transmission does absolutely depend on the polarization. And it's the Fresnel equations that tell us how much gets reflected and transmitted. We also saw that there's a critical angle when we're going from something with high refractive index to low refractive index. There's an angle above which everything will get reflected, and waveguiding is based on that, called total internal reflection. Then there's also a Brewster's angle, and one polarization can get 100% transmitted, leaving the reflected wave purely linearly polarized. So now this is a little bit interesting. It turns out, in practicality, the angle of reflection does not exactly equal the angle of incidence. And we can even look at Snell's law, and that's not exactly true. Let's figure out why that is. So we just learned that the amount of reflection and transmission depends on the angle of incidence. Well, there's no such thing as an infinite plane wave, so usually we talk about beams. Well, if we have an electromagnetic beam, we can Fourier transform that and look at its plane wave spectrum, and what we see is that a beam is actually comprised of energy propagating at all different angles. Well, if those different angles reflect differently, then when that beam reflects off of a surface, it won't be shaped like what it was when it hit the surface. So if it was a Gaussian beam when it hits the surface, when it reflects, it'll be a slightly lopsided Gaussian beam, which means it's not going to propagate the same way that it did. It'll propagate at a slightly different angle. So here's maybe a little bit better picture of what actually happens at an interface. We have an incoming wave, it hits a surface. It couples into a surface mode, and that surface mode slowly leaks away from the surface. So even the position that a wave hits is not the same. It couples into the surface wave and then reflects or transmits. And because the beam comes away with a slightly different amplitude profile than hit the surface, it actually travels in slightly different directions. And we have a change in angle on the reflection side, a change in angle on the transmitted side because of that. So here are some simulations, and what I'm not showing in this figure is we have a normally incident beam coming down here, and it hits this surface, which is at an angle, and what you see is the reflected, and on this side is what gets transmitted. Now, how am I hiding that incident beam? Remember last semester our total field scatter field? I made this entire region the scattered field quantity so we don't actually see the source. There's a couple of little grid cells right along this surface where if we zoomed in we could see it, but instead we see the transmitted wave real clearly and the reflected wave. But we're coming in at normal incidence, and there's a black and white line here, and I forget which one's which. Okay, the white is the theoretical angle of reflection, and then the black is the modeled. Very, very close, but the fact that we can see white and black here shows it's a little bit different, and the same thing on the transmitted side. It's most obvious here. We have a real extreme angle. We can see a very small angle difference here. So we're talking about less than 1 degree difference. May not be a big deal for most applications, but if you're designing an instrument, that can be a very big deal. So that concludes our discussion scattering from one interface. We want to talk about scattering from multiple interfaces. This is not meant to be a complete discussion of this, but I want you set up so that you can design some real simple devices, because we'll use these simple procedures later on to design more sophisticated devices. So one of the simplest things is two interfaces, and we would call this a Fabry-Perot cavity. So in comes an applied wave and it hits the first surface. Some of that reflects, most of it transmits. That wave hits a second interface. Well, most probably transmits, but some also reflects. Well, this reflected wave hits the first interface. Some of that transmits, some of that reflects. Well, this second reflected wave hits the second interface, some transmits, some reflects, and so on. This actually goes on forever. It gets, the amplitudes of these multiple reflected waves get very small very quick, but there's an infinite number. And what we have to do is add up all of these reflected waves and add up all of the transmitted waves to get the overall reflectance and transmittance. And it turns out when we do that, we get these infinite summations, but they're geometric series which are convergent, and we can write closed form equations for what they converge to. And if we do that for the reflected side, this is what we get. This is the overall reflection from this Fabry-Perot. And in here we have an R1 and an R2. So R1 is the local reflection at this surface, and R2 is the local reflection at the second surface, and we can calculate the overall reflection from the Fabry-Perot. And then for small reflections, this equation simplifies down to just this. And essentially what this is just the first reflected wave and the second reflected wave, and we're saying all the rest are just so small for small reflections that that's the overall reflection. So we have a Fabry-Perot cavity. If the reflections are very small, we call this a low finesse Fabry-Perot, and then the response as a function of wavelength looks something like this. And we notice that the reflection or transmission, it's basically a cosine. When we have very strong reflections and we have high finesse, the reflections and transmissions, they don't look like a cosine anymore. It looks much more like a comb filter. And in fact, this is used a lot to do things like lock lasers and do filtering. Another application of this two-interface reflection thing, or Fabry-Perot, is anti-reflection coatings. Let's say we're going from material 1 to material 2, and they change impedance. That means we will get a reflection. Well, what's one thing we can do about that? Let's shove in a different material here. So we have the same material 1 on the far left and the same material 2 on the far right. But we put in an intermediate material. And we will choose the impedance of that intermediate material to be the square root of the product of the two surrounding impedances. Then we make the length a quarter wavelength. And when we do that, at whatever wavelength we design this to be, we will get 0 reflection and 100% transmission. Now, very often, instead of impedance, we do this in terms of refractive index. And similar equation, the refractive index of this intermediate region will be the square root of the refractive indices of the materials on either side. But we still make it a quarter wavelength. And when we do that, we have 0 reflections at that wavelength. Now, when our applied wave deviates from that wavelength, we start getting a little bit of a reflection. And this is a rather narrow band match, and if we want to match over a broader band, we need more layers, and that becomes a more sophisticated analysis. Bragg Gratings. This is a whole series of alternating layers, and so very often we'll have a high refractive index layer, low refractive index, high refractive index, low, and these alternate. And we also make each one of these sections a quarter wavelength thick. So the high refractive index regions will be physically smaller because a quarter wavelength is a smaller dimension here, and the lower refractive index, where the wave's traveling faster, will be a larger dimension. But we'll make all these layers a quarter wavelength and an alternating refractive indices. And what we get from a Bragg grating is a stop band. We have high transmission outside the stop band, but within the stop band we get a rather deep band of suppression where the wave is being mostly reflected. The higher the contrast, the wider the stop band. The more layers we have, we could have thousands of layers in a Bragg grating, the deeper the stop band. And the thicknesses determines the position of the stop band. So real easily, we have some pretty simple equations here. We can design a filter to block a particular band of wavelengths. We would just make the contrast between low and high enough that it covers the bandwidth we want. We would adjust the dimensions to place it where we want, and we include enough periods to make the reflection as strong as we want. We can generalize this concept. Rather than have alternating layers of the same materials, we could have a stack of layers where they have all different refractive indices and all different thicknesses. What's neat about this, if we can say that the reflections between the different interfaces are very small, we can do a trick we did before when we were analyzing the Fabry-Perot, and we can write the overall reflection in this form. Now, we're not going to be able to do much with this semester, but I want to make a connection for you. If you've ever had any digital signal processing or digital filter theory, what you'll see is that this equation has the same exact form as a digital filter. And in fact, we can use all of the tools that folks have developed for digital signal processing to synthesize digital filters, and we can make an electromagnetic counterpart of that. So in fact, we can design electromagnetic filters to do whatever we want using those same rules and tools. And I'll leave you with a bonus thing that we may or may not do much with, but here's a different way of modeling reflection from a stack of layers. So let's say we have a transmission line circuit, and this looks like a microstrip. We have a ground plane on the bottom and our signal trace on the top. And depending on the width, we're controlling the impedance of that transmission line. So what we have are a bunch of segments with different impedances. Well, we can treat this like they were infinite slabs of material. We would analyze this transmission line, calculate its impedance, and then say, oh, we have an infinite slab of material with that impedance. And by the way, whatever distance that is, will give the layer that thickness. So we go layer by layer in our microstrip circuit, and we come up with this infinite slab of materials that we could model with the transfer matrix method we learned last semester, or it turns out we can use a technique that I'll show you here real quick. In microwave theory, we teach something called impedance transformation. And here's the quick explanation of what happens. We'll be sitting right here and we observe the impedance looking to the right. So at first we just observe whatever impedance is in the output material. Well, as we back up and we keep observing the impedance looking right, but we're backing up, it turns out the impedance changes cyclically. And that's called impedance transformation. So we'll back up to this point and we'll calculate what the impedance looks like looking to the right. And so here's our impedance transformation formula. Here's how we would calculate what the impedance looks like looking to the right at this point. Then we back up through our next layer and calculate what the impedance looks like looking to the right again. And we have a new equation. And then we back up this next layer and we look at the impedance looking to the right, and we have a new impedance. Well, finally we get to this first interface, and now we have the impedance looking into this entire stack. And so reflection is just the impedance of the input material with whatever the impedance is looking to the right, and we just look at the difference and divide by the sum. That gives us our reflection coefficient. Take the absolute value and square it, and we get the reflectance. So we can just back up and do this impedance transformation layer by layer and calculate the overall reflectance. And this is very fast. In fact, it's faster than the transfer matrix method the way we've derived it, because there's less calculations here than manipulating scattering matrices like we learned it last semester. So this works really well, and it's very simple.